Hi, everybody. Welcome to another in our series of SCiMMA public talks. This morning, afternoon, evening, whatever it is, wherever you are, we have a presentation about the ESCape project, which is going to be given by John Swinbank, Klaas, Kliffen, and Jan Grange. So with that, I'm going to hand it over to you guys, and we'll give you a warning around 5 minutes before the hour, just in case, and go for any questions or such things. People can raise their hands during the conversation, and I'll try and keep an eye on that and field them if necessary. Okay, thanks very much.
Awesome.
So please take it away.
Thanks, Patrick. And thank you in particular for the invitation and the opportunity to speak to you all today. So the background to this is that I gave a presentation at a meeting in January, which was supposed to be in Paris, but turned out disappointingly to be virtual, on ESAP, which is the science platform that's being developed in the ESCape project. Patrick heard it and so invited me to come along to your webinar, which was very generous of him. I have taken the opportunity, first of all, to invite Klaas and Jan, who I'm hoping are going to do all the hard work today while I just wave my hands and say something kind of vague and introductory. But also to broaden the scope a bit, to talk about a little bit about ESCape more generally, but in particular, zoom in on the work on the data lake and the science platform. So let me start by just introducing us. We are all working at the ASTRON, which is the Netherlands Institute for Radio Astronomy, where we work for the Science Data Center Development Program, where the ASTRON SDC is our effort to modernize ASTRON's data services to prepare us for, well, I want to say the next generation of data-intensive radio astronomy, but in fact the current generation with telescopes like LOFAR, and then preparing for the square kilometer array that's coming at us over the next decade or so. But for today's talk, we're going to focus on ESCape, which is an EU-funded project that ASTRON is a participant in. So here's a brief preview of what's coming. For the next 10 minutes or so, I am going to wave my hands in this introductory way. I want to tell you a little bit about the ESCape big picture, which runs the risk of descending into kind of EC buzzwordese, but I will do my best to avoid that. But give you a little bit of an idea of what the big picture is and what ESCape is all about. Then I'm going to hand over the reins first to Jan, who will tell us a bit more technical detail about the so-called DIOS, the ESCape Data Lake system, and then to Klaas, who's going to introduce ESAP, the ESCape Science Platform. So let me start with the kind of the fast facts about ESCape. So ESCape is an EC-funded project. The kind of really high-level mission is to develop common e-infrastructure that we can use across a range of European particle physics and astronomy research facilities. So the idea is to be generic and multi-purpose. We're not building services that support one particular piece of infrastructure, but that can be applied, reused to satisfy a bunch of different science cases. Within ESCape itself, we have about 30 different partner institutions operating across 8 different countries within Europe. And ESCape itself then is one of 5 so-called cluster projects in the EU. We cover particle physics and astronomy, but there are similar projects covering environmental research, that's ENVRI, neutron and photon science, which is PANOSC, life sciences, which is EOSC Life, and social sciences and humanities, which is called SHOCK. ESCape runs from 2019 until 2023, so we're roughly speaking 3/4 of the way through at the moment. And certainly you'll hear as we come to some of the development material that Jan and Klaas present later, all this stuff is still a work in progress. We are not presenting finished solutions, but ideas, proofs of concept, stuff that we are still very much still in the process of putting together. This is a slide that is covered with the logos of all the various ESCape partners. I put that there for 2 reasons. So the first thing to emphasize is that everything that we're presenting today is really an effort from the consortium. It so happens that the three of us are all from ASTRON, so ASTRON sits in kind of pride of place in the top left of that slide. But really all the technologies are being developed by a huge consortium with a bunch of different institutes contributing. The next thing, though, that I want to really emphasize is the kind of 10 circles arranged around the piece of heavy machinery in the center of the slide. And those are the specific research infrastructures, the big kind of scientific instruments and facilities that ESCaPE is designed to support. So I'm sure you will recognize a bunch of familiar names in there, whatever your favorite type of photon, whatever your favorite wavelength of photon or type of particle or whatever it is that you're interested in, there's something in there for everybody. And we really do try and work as a team to satisfy the needs that all those different research infrastructures are expressing towards the project. I kind of threatened you with some buzzwordese. I'm going to try and avoid it as much as possible, but some of these will appear in the names of projects or the names of pieces of technology. So I wanted to at least put them out there so that I don't necessarily expect that you will remember them all now. I hope for your sake that you have better things to use your brain cells on than remembering all these now. But so that when they come up in the course of the rest of the talk, you at least have some frame of reference of what it is that we're talking about. So just to expand the first one up top, ESCaPE is the European Science Cluster of Astronomy and Particle Physics ESFRI Research Infrastructures, where ESFRI is the European Strategy Forum on Research Infrastructures, which is effectively the talking shop where a bunch of those big science projects that I showed in the last slide get together. And we work in the context of the European Open Science Cloud, which, for want of a better description, is the kind of big funding vessel or the big structure in which all the kind of e-science projects across the EU are being organized in at the moment. And then you will hear us talk about DIOS, the data infrastructure for open science, which is Jan's presentation, and ESAP, the ESFRI science analysis platform, which is Klaas's presentation. So I apologize for the acronym soup, but I will point out then that we often talk about in ESCaPE circles, we talk about ESCaPE ESAP being our science analysis platform. And of course, you can expand these buzzwords and you'll realize the ESCaPE ESAP is in fact the European Science Cluster of Astronomy and Particle Physics, European Strategy Forum on Research Infrastructures, European Strategy Forum on Research Infrastructures Science Analysis Platform. There'll be a quiz later, perhaps. So I apologize for that, but once we've got that out of the way, we can hopefully get on to some of the more interesting stuff. So apart from generating vaguely ridiculous names, what is ESCaPE actually doing? We are organized into 5 different work packages that are kind of carrying out technical activities. 2 of them we're going to concentrate on today. That is shown in this diagram towards the bottom, the data lake, which is really the kind of bulk data management, data organization, data distribution and transport system. And then supported on top of that is this idea of a kind of reusable science platform toolkit that we call ESAP. So those are the 2 things we'll concentrate on today, but I want to draw your attention to the fact we also have the so-called OSSR, the open source software repository, which is a catalog of all the various services and software that are available in the ESCaPE ecosystem. We also have a work package that is devoted to virtual observatory interfaces, and which I'll say a little bit more about in a minute, and one that focuses on citizen science. I won't go into any more detail on ESCaPE citizen science activities, but it's worth saying that ESCaPE regards citizen science as kind of a fundamental part of our activities, both because we just think it's a good way to kind of bring the science and engage the wider community in the scientific activities that are being carried on as part of ESCaPE, but also because it's actually a great way to answer some of the scientific questions that come up. I mean, the projects like Zooniverse have been successful, and we would love to capitalize on that. So to finish off, I'm going to say a quick word on the OSSR and the virtual observatory activities before I hand over to Klaas to dive more into hand over to Jan, sorry, to dive more into some of the technical details of the data lake. So the software and services repository, we're not going to talk about the technical details of it today, But the idea is that this is a common repository for the software that's generated across the various ESCape infrastructures. And the reason that we care about that is twofold. So one is to make that software available today, so that scientists who are using the ESCape Science platform, who are using other pieces of ESCape tooling, have access to a kind of a curated library of software that is integrated with, known to work with the various different services and facilities that are available across the ESCape system. But also, and perhaps even more important than that, this is a kind of software preservation effort. So this is integrated with the Zenodo system to give us long-term storage. It's automatically issuing DOIs to the pieces of software that get distributed, etc. We try and make this as easy as possible for the software developers. This ESCape project provides you with snippets of code that you can dump into your CI system, whether it's GitLab, GitHub, whatever, that will automatically upload to our software repository when you tag a release or etc. And we provide libraries, the so-called EOSSR library, which is a Python library for working with the contents of this software repository. And then, as Klaas will refer to in a few minutes, this is integrated with the ESAP platform itself, so that as you were using ESAP to discover and work with pieces of software, the backend that's powering that is this software repository. The other thing I'm going to mention very briefly is the importance that ESCape puts on the open standards, and in particular the virtual observatory. So the VO is sufficiently important to ESCape that it kind of qualifies as a work package in its own right. And that work package really has the twin goals of driving VO standards into all the other ESCape tools. Wherever possible, we want to be using these kind of open virtual observatory standards, but also in contributing effort to virtual observatory standardization efforts to push them into supporting the kinds of technologies, the kinds of systems that ESCape is interested on. And we've had progress there in, well, metadata for solar physics, for radio astronomy, etc. This diagram you can see on the right of this slide is the standard VO architecture diagram that I think many of you will probably be familiar with. And I have blobbed little yellow dots on all the kind of VO standards that are being touched in one way or another by the ESCape infrastructure, so that we've had some engagement with. Then the final bullet point there, I have written education, 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 and that's because one of the things that ESCape has really invested heavily in is summer schools, outreach, education, in particular on how to bring virtual observatory technologies to the kind of European scientific community. That's my high-level overview out of the way. I'm happy if anybody wants to jump in with a quick question now, I'm happy to take it. Maybe yell or raise a hand. Otherwise, I will hand over to my colleague Jan. Jan, I think the easiest thing is if I keep sharing slides, but you can yell at me when you want me to go to the next one.
Sounds like lots of fun. Well, I don't see questions, so I'm quickly going to continue then. Well, hi, I'm Jan. I'm going to talk to you about the scientific data lake. Let's experiment with the yelling. Please, next slide, John. Thank you. So I wanted to start with catching a bit of context. So basically, I call this the current situation, but I mean it's sort of looking forward on how are we going about storage of data from the kind of instruments that well. I mean, we also, of course, have at ASTRON, but I think it's a general problem in radio astronomy. So, of course, we see that data sizes are increasing. So, well, there's different ways to store a lot of data. One of the ways that actually we use and that we see you getting popular is distributed federated storage. By that, I just mean that you have several places where you store data, and those places are not necessarily owned by yourself, but maybe by national supercomputer infrastructures or other education infrastructures. And so, of course, one of the things that you need to do is to need to know what is where. And right now, well, I think this is more of a bit of an honest way of saying how we typically do that is we sort of decide by hand, like, okay, the data goes there, and then we put it in a database and we keep track of it. And I mean, sure, things go well, but it doesn't really scale very well. Sorry, next slide, please. Let's see how long it takes for me to not ram space before saying that. So, well, one of the things, of course, we in the work package 2 of Escape. So one of the things that you see is well, it's obvious that certain experiments also generate large amounts of data volume, and well, radio astronomy does as well, but probably astronomy in general. And so what you see is that the type of infrastructure is the same, and what I mean by that is it's also distributed infrastructure storage in well, of national centers. And so basically the Atlassian experiment has developed an architecture for data management at this scale. And so that's what we call the scientific data lake in this context. I will have an intermezzo slide on this later. And of course, I mean, one of the things is we are different domains. So part of the work we have been doing in the work package is actually on one hand to try and familiarize us with this specific architecture, but also to come up with what works for our domain and what doesn't, or what isn't ideal for our domain. And the nice thing is, of course, that developers are also part of the project. So there is also some feedback into the Rucio development team to say, hey, this is the functionality we that would be really useful for example, astronomy. Click. Yes. Okay. So basically the background idea, and I'm sure that lots of people are familiar with that, but I will still explain it, is rule-based data management. Now, in this specific context, I did something which may not be the first thing you'd expect for someone who's colorblind, but I decided to pick color as the main property of storage devices. Of course, in real life, you have a storage device that can be at a geographical location or has properties, right? It's fast storage or slow storage, etc. And I just decided to simplify that. So for example, we have a telescope and we define the rule that all the observations of surveys will have to go to blue storage. So when you observe a survey, then it will go to, in this case, location 3. Click, please. And now I hope that I used the right color, but else just think that I wrote down green. If we define that pulsar observations, for example, have to go to orange storage, well, then we make an observation of a pulsar, and again, the data management system will put it on orange storage. And I have one more complex rule. Yes, no, click, please, yes. I mean, another rule you could define is, of course, say, if we have FRB detections, that's really cool, right? So we want to make sure that the data doesn't get lost. So we want to put it on 2 locations. We don't really mind where it goes. So again, that's another type of rule you can think of. So basically the fact that if you click once more. So basically, right, the idea is you define the situation that you want to achieve, and you don't necessarily define how you want to achieve it or how you want to make the copy from A to B, etc., etc. That I think is the whole idea of the rule-based concept. Next slide, please. Yes, so now we go into the intermezzo, right? I didn't invent the name scientific data lake, so I will not necessarily take responsibility for the confusion, but we all in the project realized that the name is a bit confusing because the word data lake already has its own Wikipedia page even. So I just wanted to stress here that, whenever I say data lake, I actually mean this specific architecture that we're talking about, and it's not actually at all what you see here on the Wikipedia definition, which is much more of a repository of data kind of thing. And I think that's good too. I've had so much confusion in public talks and seen that as well, that probably just wanted to stress that explicitly. Please click on. So now what actually is the infrastructure that we're looking at? So it consists of several components, of course, several tools. So I actually on the top you see 2 images that show different views on the architecture on the design. So basically the right hand side I actually start with that because it's a very broad architecture. So what you see there is the fact that you have sites with storage, which all have their own types of storage and their own types of baby compute and that sort of thing. And you try to get the data that's on there in sort of a uniform way to any type of processing. And you see typical examples of processing on the bottom. You can probably see that talking about classical grid data processing infrastructure shows that, again, there is some background in particle physics here. But of course, the infrastructures can be pretty different. So on the left, you actually, what I like is that it's sort of the core components of the architecture. So I will be focusing a bit more on Rucio and what follows. So I will not give it too much attention on this slide, but I want to give attention to the other components there. So FTS basically, well, FTS is a transfer manager. So it's a tool that runs somewhere, and you can just tell it, I want to copy data from location A to location B, and it keeps a database and it takes care of retries and failed transfers, et cetera, for you. And so that really works together with Rucio, right? I mean, there's not much data management to do if you don't have a way to actually get data from A to B. Then there is the caching layer, basically Xcache. So I decided to also add the logos of the X-Root team there, because Xcache is highly coupled to X-Root. And again, I mean, right, all these tooling is stuff that is certainly not, well, especially anything but Rucio. We haven't really written too much on that in the context of the ESCape project. So Xcache basically is a caching layer, so you can do some prefetching and fetching parts of files, etc., etc. I have to admit that we, with our use cases, haven't tried that too much yet. And then on the right-hand side, there are two. I would say that those are more the facilitating services. So first of all, there is Crick, which is basically an information system. So it's basically, you can see it as a database of all the components that are there in the data lake, like what storage do we have, where is it up, is it down, is it broken, etc., etc. Or is it in maintenance? And IAM, which is basically an AI system that is used to that we use to do federated identity management. So you can log in with your own credentials, and of course, then there's some group management in there that makes sure that towards all of ESCape, actually, you are seen as a member of a certain group. You can also log into ESAP through IAM, actually. Next slide, please. So I just, I like John's slide with lots of logos. So I just wanted to brag about having also a lot of logos in our context. Well, I mean, so now we'll focus on Rucio, just also showing that there is quite some, well, there's a lot of involvement of Rucio from all sorts of different instruments, institutes, etc., etc. Again, it's more of a context thing. So I would propose to go to the next one. Yes. So I just now, I'm going one level deeper, looking at actually functionality. So what are the typical features that we have in what we're looking at? Basically, I think this list is really ordered in advancedness, and I will show you later also what I mean by that. But so of course the file and dataset catalog, knowing where the files are is a pretty fundamental part of a data management system, I would say, and being able to transfer between facilities, or at least initiate transfers between also different types of storage is also probably quite important. Having interfaces to that is also something that you may want to have. And then the further you go down, the more I think that are probably optional, but very nice. Of course, some things you can actually say, hey, those are really important for us, and others are less. And if I can go to the next slide, you can actually see that it's typically set up as a bunch of services. So there are clients, a server that has different components. Then there is, of course, the core, but then there are the different daemons, and the daemons can I mean, they basically bring the functionality. So you can basically, I would almost say, pick what daemons you want and what not. I also wanted to show you something about the creativity of the development team. So if you click once more, we'll actually see the name of all the daemons or a bunch of daemons, actually. I'm not sure if those are all of them. I would almost challenge everybody to find all the themes in there, but it's very funny to see that there are some somehow orthogonal themes in here, and some just very practical names. I don't think the auditor is per se someone from the Greek mythology, but I may be mistaken. Next one, please. Okay. So again, the concepts, I just wanted to go again a bit more on to how it conceptually we look at it, or how it would work. So the first of all is, of course, the expressive metadata, and like having meta. Well, again, I think it is pretty obvious that if you want to define rules that act on data, you need to have a decent metadata for that. So the storage elements, which is basically the endpoints, right? It's an endpoint that speaks one or multiple protocols which can be HTTPS, it can be S3, it can be grid FTP, it can be whatever. All the storage I will I will bluff here. Anything that FTS can speak is of course supported here, but I'm not sure whether that says a lot to the people who do not know FTS that well, but it speaks several protocols. And so, of course, a storage element has multiple metadata types. Is it tape? Is it disk? Is it how much free space is there? Where is it? Because you can actually also think of rules where you say, I want my data close to this location. Currently, and I think that since that is actually a significant, that is actually a task within the DOS work package, I have to at least mention it, is we are actually also looking at making the concrete storage device name. So really saying, oh, this thing is tape, this thing is disk, this thing is SSD, to move to more of a quality of service type of description of places. So also again making the I think this all fits the whole discussion about, you want to be expressive in terms of the how and not certainly about the what. So you say, I want my data on cheap storage. But to a certain level, I don't really mind whether that's tape or that someone actually does something really cheap. That's not tape. That's actually... Next slide, please. And then, of course, there is data. You can't really get away with not talking about data here. And so here I think the important bit is again also so the storage elements have their metadata and the data sets have their metadata. And the metadata is basically described using I would say 3 types of attributes. Of course, there's the standard attributes which you get from any LS on any file system, right? Maybe checksums are a bit more complex, but that kind of stuff, file sizes, creation dates, etc., etc. Then there is data attributes, and here also again you see that of course it was originally developed in particle physics things, because you have things like number of events, the run number, the task ID, etc. I don't think that those are very useful for us, but there is support for having JSON documents together with data that actually define custom metadata. And there is also actually a plugin mechanism that I will also get back at that later in the work that is currently being happening. Then there is the, of course, the data management attributes. A typical example there is if you say, I want a copy of this data set somewhere in Amsterdam, and I want it to be guaranteed to be there until the 26th of November, you can add a metadata key saying, so on the 27th, it should be deleted, or you just say, I guarantee it until the 26th. And after that, you only delete it if you need the disk space, right? That's sort of a typical metadata key that has to do with data management itself. Next, please. So then next thing to actually have a look at is the data hierarchy. So I think there is a few concepts here that are relevant. First of all is that everything is what you call a data identifier. So whether you have so I'm going to make the conversion here to normal file systems for a moment, because that's something that I at least have a better feeling of. If something is, let's say, what you would call a file, or something is what you would call a directory, those are all one type of unit in principle in the system. And so actually the namespace is pretty flat. So there is one thing that is the scope. So there's one scope, and under that you have, it could be files, it could be data sets, and it could be containers. And so the idea is you have files and you can put those in data sets. So here what I did is actually I have in my Rucio thing, I have 3 times 3 files, and I combined a bunch of files to be an observation. So I have 3 observations in 3 files in observation 1, 3 files in observation 2, 3 files in observation 3. And I could, for example, make a container of observation 1 and 2. And then if John clicks, you will see that, I hope. Yeehaw! And so that's nice. And I always use the example, being again from radio astronomy, that this could, for example, be that observation 1 is actually a target observation, and observation 2 is a calibrator that you want to use to calibrate the target observation. But you could also think that this calibrator can also be used to calibrate observation 3. And you could also create a container around 2 and 3. If you click, that will magically appear. So I actually like this concept that you can sort of combine multiple blobs of data, and that one blob of data can be part of a different container. And so basically, right, this also offers users to say, I want to download data combination 1, and then it downloads all the files that are part of that combination, or data combination 2. And actually, I thought, you know what, you can also put containers in containers. So I also, for my example, created the container with everything, which you will see if John clicks again. Yay! So if you want to download all data, you could actually do that as well. And so again, there is metadata at every level here, right? And of course, it is obvious that probably that containers and datasets only differ from each other in terms of what the actual metadata fields are that are in there. Well, in the file naming, I put an example on the bottom right corner because it's probably the easiest way to explain this by showing, and then I would like to click again. So again, of course, there's always a bit of this confusion. Okay, now I have this very fancy system, but I have files in my data lake. Now I actually want to do some work. That's always a very, then you get users who actually want to do something. So of course, the Rucio clients have an upload and a download command, which basically automatically gets the data from where it actually is stored. But in principle, the system doesn't really mind that the data can also be downloaded behind its back, as you call it, or uploaded behind its back, as long as you register it after you have uploaded. It will not manage data that you put there and then never tell it exists. So actually there is the direct access. You can do a download, or you can actually move it to a place that can be directly mounted. Actually, in the data lake as a service, which I will mention later, and that Klaas will also show, what they do is basically they have a fuse mounted file system where they just create a rule to copy the data to, and that also works. I think one thing is that I always find confusing, and again, I think that this would probably not have happened if it would have been an astronomy originating project, is that they have an algorithm to distribute files over directories on the actual file system. That has to do with the fact that if you put all files in the same directory, at some point you get issues with inodes and, well, stuff. I don't even know what the issues are you get, because we never really do that. We actually have nice directory structures. So that's something you have to keep in mind when you actually want to manually manage or manually put data and get it on and off the system. On the other hand, you can actually configure endpoints to just behave as you would expect a file system to behave. Next slide, please. So for the interaction, I think I really have, well, during the project, we've seen several ways of doing it. So of course, primarily it's a daemon that has a REST API. So if you really want to, you can actually use curl to do stuff. And actually in ESAP, the query functionality uses the REST API, basically. That's why I wanted to explicitly mention it here. Of course, there's a command line interface and a Python library. What I really liked actually was that I mean, again, that's not very, it's not rocket science when you think of it, but that the command line interface is really just a wrapper around the Python library. And there's a lot of stuff you can actually, if you want to add the library to your workflows, it's fairly easy to just, have a look at how certain commands are issued using the CLI and what it actually does under the hood. And I'm not sure whether I should say things about documentation, but I think that's much better documentation than the documentation itself. Then of course there is a web user interface, and so one thing that we really did during the Escape project, that also was there was actually a Google Summer of Code student working on that. It's actually to work on a Jupyter notebook that gives access to scientific data lake. So that is really targeted at end users much more than data manager or fancy certain people who know what they're actually doing. And it is actually really nice. And if you click again, I just wanted to show one example of the web user interface, because when I started in this was the first interface I started using, because it's nice and simple. It was very hard to actually find a file on the data lake that was mine and still existed, but here is one. So what you see here actually is typically the metadata you have for a file. And on the bottom, you can actually see also that there is a copy of that, and you can actually download it. Now, I think in this case, clicking on the download button will actually stage it to a WebDAV activated storage device, and then you can download it. So there is, of course, this concept that that's what a web UI does actually quite nicely, I think. Next one, please. So what's ongoing? So I think one of the ongoing developments is in also looking past the Escape project is that the SKA, they have embedded the developer in the Rucio development team. And also they are actually, they or we, depending on how you see SKA, is a group effort of different institutes, I guess, prototyping with Rucio for the regional center, science center data management. And one of the things that they have been doing, and I think that's very interesting and relevant for astronomy, is actually that so basically the system where you say, you know, I do not want to say a rule per file. I just want to find one simple rule that acts on specific metadata. That all works fine, but it only knows about equalities, and it only knows about the metadata that's built in. So there's actually two things that they've been working on, and that are I think it's already even implemented in the last version, or it will be implemented in the next version. Is these two things. So now you can actually say, you know, I want everything that's in the galactic bulge to go to Amsterdam, right? So you have an array in a DAC, you have a smaller than concept. So, and that of course would make life much nicer, because you could actually even define rules that are astronomically probably relevant. One of the future things that I also find relevant is looking at what the performance would be if you would basically write a plugin that takes the metadata from a database, because right, you have an observatory that already has a database of all the properties of your files, and if you make a copy of that, then you get 2 sources of truth, or 3 or 4. It's probably at least worth investigating how much how little will break if you do it directly, the coupling. Please, next link, next slide, I mean. Thank you. So I thought, you know, that also with talking like this is a bit of a technical place, so, you know, I can imagine some people would like to, you know, get their hands dirty or do stuff. So I think a few primers on how would I get started if I wanted to set up my own copy. So, well, of course, FTS is one of the concept, one of the tools that is required. Now, I think actually for FTS, the nice thing is that there are several public services, and I think for especially smaller instances, you can just rely on CERN having a public server there that can talk to any endpoint that you define. For the rest, it's fully open source. There are Helm charts for deployment on Kubernetes. I think both on actually the Rucio repository, there is one also in actually the things the SKS set up. And actually there's also a Docker Compose file that just, you know, brings up a few daemons in Docker, and they talk to each other. Next one, please. The last one actually for me. And I thought I'll also put in some resources. Of course, the client, we actually put the client in a container, and not only the client, because the client itself is great, but also having all the requirements to actually be able to upload and download stuff, and of course it's an Escape thing, so all the settings will be set up to point to the Escape instance, but since it's a single configuration file that can be changed manually, that could actually be something that people could look at, and always happy to support, I guess. And one thing I would say on the Escape wiki, but then I found out it's actually not even on the Escape wiki, but there is in several meeting notes, there are some data challenges that we did, and we here, I mean the different instruments that are involved in the project. We did some challenges to, you know, let's try out this, or we got the request, oh, make a file and put it on there and see how far you get. So I think there was also, it's actually a very nice starting point for people who may want to have a look. I think this was my last slide.
Yeah.
Thank you, Jan. There's a question in the chat. I don't know. I want to make sure we have enough time for Klaas's presentation as well.
Yeah.
So maybe we could just do 1 or 2 quick questions now.
Sure.
Although that first question may be a long one, which is about existing solutions. But if you maybe if you could just address it briefly, and then we could see if there's time at the end.
So I think that's a good question, and also I think the question is, of course, also these things time progresses, right? After you do things. So I think also, for example, in the SKA, we are looking again at alternative solutions there. So of course, the Rucio has not been developed inside the ESCAPE, right? It has been brought in as technology from by one of the partners in there. So I in that sense, I can't really answer the question in that way. So I don't really know what the exact shortcomings are of all the alternatives there.
Okay,
that's the short answer.
Maybe, and then Rich has a question.
Yeah, and it's quick. How a great presentation, thank you. How are credentials managed? You know, it seems like in these federated things,
Yes.
you really have a credential management issue, and so maybe you could talk a little bit about that.
Oh gosh. So one of the things that we have been pushing for a lot inside in the project, and again, it's the astronomy side that has been pushing for this, is anyway going for moving from the X509 certificates that are commonplace in particle physics to basically OIDC tokens. So I think that already was a whole right, because else your credential management is much more in getting your certificate. So we are basically connected to EduGain, I think it's called, the international thing. And so basically there is some automated synchronization between the Rucio and the IM, which is basically the when you log into EduGain, your profile gets coupled to IM, etc., etc.
So I get the authentication. Let me just like how do I federate my AWS credentials with my IM credentials so that your metadata is referring to things that actually can be transferred?
I'm not sure if AWS credentials are. So in that sense, I'm not sure how much of the broad, in the broader sense, how much of the cloud's credential or external. So there is federation in one direction, right? You can log into the system with your external credentials, and I think you're talking about the other way around here.
Okay,
well, I just don't. It's okay. Yeah, we can talk about this offline.
Yes,
I think
yes,
I
please.
understand
Yes,
what
please.
you're telling me. Okay, thank
Yes.
you.
Yeah. Okay. Sorry, Rich. I just want to make sure we have time to hear from Klaas. So please, Klaas, go ahead.
Yeah, thank you very much. I'm Klaas. I'll make it a bit shorter than expected, so I will skip some parts of it. So the current situation, Jan already told us a bit. There is data scattered across different archives, especially the data lake, which Jan just mentioned, but also there are a lot of existing archives. For example, ASTRON has the Alta archive, but also FEO services exist. And what we try to do with ESAP is essentially all group them together. And essentially, ESAP is a toolkit for building a science platform. It's not a platform by itself, and essentially provides a single front end for data, software, and the compute landscape. It's not specific for astronomical datasets. It's also used for particle physics, and it can be extended for other types too, for example, natural language processing. Essentially, what we try to achieve is a very extendable plugin infrastructure. And it can be configured to be either a central hub, as we have in ESCAPE, where it can reach any service within the ESCAPE infrastructure, but it could also be configured a bit smaller for a project. So essentially, we have three components: a user interface and API gateway, and we have asynchronous workers, which are still in progress and are not yet in production yet. So essentially, you have on top the end user, which only interacts usually with the GUI. And behind it, it's the gateway, which has the configuration which allows you to enable certain connectors or not. So on the left side, we have all the catalogs, and these are all specific, have all kinds of query connectors in there. A query connector is essentially a translator between the general interface provided by the ASAP API gateway to the specific standard, for example, with the VO, but also Universe and other catalogs in there. And we try to provide services to connect your data to interactive data analysis platforms such as Jupyter Hubs. And of course, you need to search or you can interact with Rucio to make the data available again. And there are also batch processing systems. For example, the British partners of ESCaPE, they have access to Direct, which is a specific high performance computing cluster. And there we also want to integrate with that to provide them access via ESAP. Essentially, the customer journey looks like finding data, finding software, and finding computational resources, combining this all together so that you can perform science, and then making the results available again in ESAP. So this is the homepage where we have all the archives configured. And if you go in there, you can actually see what kind of data sets are available in that archive. And the next screen will show you like a quick tool where you can perform a cone search in this case. You can already see that you can make the data available by downloading it to your local computer so you can check it out. But preferably you will want to, you can also inspect it as a thumbnail. But you can also, let me see if I can, you can put your data in a shopping basket. And this is a bit similar to what we have in, for example, Amazon, where you can select products, in this case, data, which you find interesting. And this is really the core of ESAP. Everything you do within ESAP is around this shopping basket, where either you put data in there or you make sure that this data get pushed to the interactive data analysis platform, which you want to interact with. So now that we have selected some data in there, you can select workflows. These are all queried to the OSSR. Here I search for some aperitif workflows. And the next step is to find actually infrastructure which is compatible with that. This is all being expanded to also support containers and also later remote desktop environments. Essentially, when you click deploy, you will get a new web page. Some of you may be familiar with MyBinder, which is a free service where you can essentially pull a Git repository, which will build a container for you, and then launch a Binder Hub instance where you can access and perform your analysis. And there are also available private Binder Hub instances, which we are using within ESCaPE, which can, for example, link to more powerful hardware or have access to GPUs for processing. We're still in progress. What I already mentioned a bit is batch processing. So you just find your data and you can launch the job and you get notified when it's done. And the results will then be sent back to ESCaPE or ESAP. And we're also looking into making remote desktop applications available. So Topcat or Aladdin Sky Atlas, because the data gets too large to move to your local PC. So let's move the software to there. One of the things we also have to take into account, of course, is data locality, because the size of the data makes it sometimes silly to move the data around. We are planning to have warnings in there before making or committing to a job where probably the data transfer will not happen. This is an example of how you would interact with the shopping basket in a Jupyter notebook. Essentially, you will install a certain Python client, and that will be able to connect. And in the current notebook I have here, you will get the credentials for accessing that shopping basket via the Jupyter Hub instance. That will use the same IAM instance and will make the tokens available via an environment variable. So it could be used inside of the containers. Of course, this is not very nice to have it all in there as a cell. Sometimes it's better to actually make it already available on the system. So Jan already mentioned a bit about the data lake as a service notebook. Here you can see, for example, the same LOFAR ASTRON Grange file, which is currently not available. And it's very easy to make this available by hand. And essentially what it does in the background is make a rule so that the data gets replicated to the local file system. So this is mounted to a fuse mount and then inside the container again. And then later you can add it as a variable so that when you access it in your notebook, in in this case some name, it will actually point to the path where you can actually open the file, extract it, and perform your analysis, what you want to do with it. So after being done with it, you of course want to make the data available again. It's still in progress. There is a milestone where we reach that we can actually upload the data back to the data lake. So it will get its own DID and you can reference it again in ESAP. However, that storing those references back into the shopping basket is not done yet. And we're also looking into minting DOIs so you can actually use it as a reference somewhere. Then we also have, then I will take a little bit a step back. So we have the web front end. It is a simple React app. And we separated UI from the backend, which allows you essentially to really rebrand your own ESAP. So in this case, at ASTRON, we made the ASTRON Data Explorer, and we added some other nice components which might not be useful for all ESFRIs. But for us, it is to have a elegant sky view in there so we can actually see where the data is located on the sphere of the heavens. And the backend is mainly a Django project with the Django REST framework. And what we try to achieve is to have all components as a portable Django app. So if you want to set up a science platform, you just create a new Django project, install the specific applications, add the configuration of, for example, the archives you want to have, and then you can actually work with it. And it's quite easy then to configure it. And one of the things which is still in progress is actually to have some asynchronous workers. And that's mainly because some of the work, for example, performing a query can take quite some time. It could be that it is taking a longer time because there are many results, or it needs to perform some operation which takes some minutes or hours. And usually a web framework cannot respond or needs to respond within a certain time limit. But one of the more interesting things which we are looking into is also orchestration, which is essentially setting up those IDA systems where you don't have to manually download your data anymore. So essentially you have the ESAP GUI, where you select all your data, software, and infrastructure. You click your start job. Then ESAP will kick off a worker, which will have different kinds of plugins to access certain storages. It could be S3, it could be the data lake as a service. And what we will try to do is make the data available to the compute plugin. It could either be a public link where it will need to fetch it, but it could also be like a local path where the data is made available after a Rucio plugin, for example, has made a rule and all the data has been replicated. And then a compute plugin will actually perform the starting of the container or a new node or a Jupyter Hub instance, and then you can perform your site, or you get a link back. That will then be posted back to ESAP, which will post it back to the ESAP GUI, where you can actually click it and you'll be redirected from ESAP directly to the interface where you can perform your analysis, or you can look at the results and see your data. And essentially, that is something which is not yet in place, is still currently in flux, but it's something where we are heading in the coming months. And that's mainly the short story of ESAP.
Thank you very much, Klaas. And sorry, we didn't have quite as much time. Does anybody have any questions for Klaas to start, and then for John or Jan as well?
I have a quick question.
Oh, please go ahead. Sorry.
That last slide there about this spawning of jobs and orchestration, it kind of reminded me of Wholetail a little bit. Have you seen Wholetail at all to compare that?
Not yet, actually. So I would be quite interested, actually.
Okay. Yeah, maybe I'll send you a link, because I couldn't tell how much they overlapped or not, but it sounded similar.
Okay, thank you.
Thank you. Any other questions?
While folks are thinking of questions, I'll just point out, I hope you are seeing that I've just stuck up a slide with some URLs to some of the things that we were discussing today. There is obviously in the project with the scope of ESCape, there's a bunch more stuff that we couldn't cover. And I have to say, Klaas did an amazing job of talking really quickly, but certainly in the ESAP, there's plenty of scope for more things that we could talk about. You can find a bunch more information on these pages, and we are very happy to hear from you. I think our email addresses were on the first slide, so you can see them on the recording, or we're happy to share the slides. Please do drop any of us a line, and we'll be more than happy to either just answer questions by mail or point you at more resources, because there's a lot of written words on this stuff out there.
Okay, well, thanks a lot. And if there are no final questions, I just want to thank all three speakers. It's very interesting. Even finding that some of this is apparently used by places that I work with, but I don't even know about it. It's always exciting. I'll try to have to understand what POSI is doing with this, rather than trying to reinvent everything there. But yeah, so thank you very much for the talk, and we will post the recording when it is ready.
Sure. Well, thank you for the invitation. It was a pleasure talking to you.